It is part 3 of section 16.2. So far, we have learned line integrals of scalar functions. Now we'll consider line integrals of vector fields. Let's see the recall. Earlier in Calculus 3, we have found that the work done by a constant force, F, in moving an object from a point P to another point Q in the space is W, is the same as F dot D. D is the displacement vector. We can generalize this concept for the work done by a force in moving an object along a curve. In general, if the curve is parameterized in this way, R of t and xt, yt, zt, so it's a curve in the space. Now t is moving from A to B. Then the work done by a force F in moving an object along the curve C is defined in this way. The work is the limit of Riemann sums, but for each one is exactly this formula, and force dot the displacement vector. Let's see this figure. Okay, now this is a curve in 3D, and for given partition, this one, so that rather than this real displacement, we may approximate this displacement by the vector. That is, now there is unit tangential vector t times the length of this portion of arc length. So that is exactly that one, t and delta si, which is the local approximated displacement, and this is force. So these are summed, so that this is a Riemann sum, and work is the limit of these Riemann sums. In integral, we can write in this way: integral over the curve, and f, okay, this f and t dot product and ds. So that is the definition of line integral of vector fields. Now, we'll try to deal with this one and conveniently in calculation. What is the unit tangential vector? We can get it quite easily. Now, once curve is parameterized by R, then R prime is always the tangential vector. So divided by its length, we can get unit tangential vector. That means it is a tangential vector having length 1. Now, ds, we already know that arc length element is r prime length dt. So we combine them for this term. Then w, the work is integral along c f dot t ds. Now t, capital T, is r prime over its length, and ds is now r prime length dt. And we can cancel this one there on. So we reach at this formula. and we may write this one in this form. So that is definition. That is calculation formula. Okay, let's see here official definition. F is a continuous vector field. So we don't have to think only the force. Just simply we generalize it so that F is a continuous vector field and on a smooth curve C and parameterized by R of T. Then the line integral of F along C is defined in this way. So along integral over C, F dr is, that is definition. We consider only tangential direction of the vector field, and integration is done with arc length element. Now in practice, we can get it by using this formula. Integral over a to b f of r dot r prime dt. So we say that, and once we consider F is of force, then work is the line integral with respect to arc length of the tangential component of force. That is exactly tangential component of the force. Okay. But anyway, in general, F doesn't have to be force. Just any vector fields we can define line integral. But the behind the physics, physical application is the computation of work. Okay. The last term in this equation gives a calculation formula. That is the definition. That is for calculation. Now FDR can be written in this way. So here F dot T and ds, okay, and integrals with respect to arc length now S are unchanged when orientation is reversed, because as arc length is not reversed. But however, for this the line integral of vector fields, we have this. Once you try to get integral through the reversed the curve, then there is negation of the original curve in integral. Why it is happening? The reason is, if you consider this one, then looks like it's not changing. However, now here, once you are moving for curve, for example, that direction, that's a C, then unit tangential direction is that direction. But if you consider, for this point, if you consider here minus C, the other direction, then the corresponding unit tangential vector is that direction. So that even though it is not changing along with the orientation of a curve, this term is changing. So that overall, if you try to get line integral over reverse the curve, then that's the negation of the integral over original curve. Okay. Let's see the problem. Evaluate and over C integral f dr, and f is given in this way, and C is given by this parameterization. Okay. Now, and t is moving from 0 to 1. So we have to get an fr and dot r prime. That's what we have to get. And then that can be integrated from 0 to 1 with respect to t. That is exactly the calculation formula, right? What is f of r? Okay, originally f is xy, first component, second component, the final component. So that f of r is for first one, xy. X is t, y is t squared. So that's t cubed. And yz multiplication is t to the 5. And then now the final one is zx, z times x, which is t to the 4. Okay, and r prime, that is 1, and 2t, and the final one is 3t squared. Okay. Now this is dot product, so the t cubed plus now 2t to the 6 and plus 3, okay, that is a t to the 6. Right? So we have t to the 3 cubed and plus 5 times t to the 6. So the given integral can be written as here integral from 0 to 1. T is from 0 to 1 here. And f of r dot r prime is this one. So that is t cubed plus 5 t to the 6 dt. From here we'll have 1/4 plus from here we'll have 5 over 7, right? So you can simplify. You can make one fraction here, 28, and that is 7 plus 20, so that is 27. Okay, that's the final answer. Okay. Now, for 2D, we have here an earlier in definition for two-dimensional vector field. We try to make this notation. Now, for 3D vector field having 3 component PQR, integral over C and FDR can be written in this way. Okay, so it is a kind of a notation. Let's see the problem. F of xy, the vector field is given in this way, and C is the parabola y equal 1 plus x squared from -1 to 1 2. Use a graph of f and c to guess that the line integral is positive, negative, or 0. Okay, let's try to visualize the curve. Okay, that is now y equal 1 plus x squared, so that it's moving like that. So it's from, that is now -1 to 1, and it's moving there, and this is beginning point, and that is end point. Terminal point is height is 2, that's 1, right? Okay. Now we'll use this graph to guess the integral is positive or negative. Okay, Now, how about the vector field? That one is, in fact, the vector field so that for each point xy, this is outer unit vector. Because once we use this boldface x to be x and y, then that is exactly now same as x over x length, right? So that this is a unit vector in x direction, which means that outward from the origin, outward unit vector for every point. That's the vector field. So if we try to visualize a vector field for a general point x here, then how about now minus x here? Okay, then that one will be, the vector field must be this one, unit outward vector, that is f. And also, once you think here, then there will be again, now that is f. Now, in line integral, we are considering tangential component. So here now, the unit tangent vector, okay, let's try to use another color. Unit tangential vector is like that. And for this one, this point like that. But if you are considering, okay, it's too long anyway. I made it too long. Must be same length. Okay, anyway, it's like that. Okay. But if we consider this one negative direction like that, then this shape and that shape is same. Basically, they are symmetric, which means that now once we consider these two obtuse angle dot product and here the dot product, then they'll be the same. However, the original one, that t, the unit tangential vector, and along with this one, now this value is negation of that dot product. So for x, if this is, okay, in fact, there's a negative, then for that one, the value is, okay, this is positive and this is negative. But also the same quantity, but only the difference is a sign. So that in x and minus x, these two values have it's a negation of the other one. And for every x from -1 to 1, you can see that this x as an arbitrary point between 0 and 1, x and minus x. We have f dot t. So we can say in this way, at x, and of course at the moment we have y, but that one is the same as, now here, consider that one, f dot t and minus x and y, then we have to put here negation. So if we try to get integral over whole curve, then we cancel out each other so that eventually we can conclude that that must be 0. Okay? So pictorially, we can figure it out. Now, in part B, we have to evaluate the integral practically. In order to do that, we have to start with a parameterization. The curve is made here, y equal 1 plus x squared. So that once x is t, then y must be 1 plus t squared. So that is parameterization. And t is moving from -1 to 1. So to get the line integral, we have to have this one. again, f of r, okay, this is now part B, dot r prime, right? Always we have to get this term. And now x is t, y is 1 plus t squared. So that f of r is, okay, on the top we have t because it's x, and divided by square root of x squared. X is t, so the t squared. Y is 1 plus t squared, so that 1 plus t squared and squared. And second one, and rather than x, it must be y. Y is 1 plus t squared. And bottom must be same, the same radical. So we just put radical here. Inside, they must be the same. That is fr. And how about r prime, which is 1, and derivative of this one is 2t. Okay, so we have dot product, and bottom will be the radical, and then top, this multiplication is t, and now this 2 multiplication is here 2t and 1 plus t squared. So that is 3t on the top and plus 2t cubed and divided by, okay, let's try to write down the radical along with the function inside. That is t squared plus now 1 plus t squared. Okay, we got this dot product, so that the line integral must be integral t moves from -1 to 1, and that function 3t plus 2t cubed. Okay, let's write it a better way. 2t cubed, and then bottom is square root of t squared plus 1 plus t squared and squared and dt. Okay, if you try to find the antiderivative of this function, then it's not easy. However, we can get the solution. It must be 0. Now, we can do this way. The interval is symmetric, -1 to 1, and this portion is even function, and this portion is an odd function. So even and odd functions are multiplied, then the multiplication is an odd function. Symmetric interval, odd function, the integral must be 0, right? Okay. Okay, now the answers are given for number 1. Okay. Now let's see number 2. Now, okay, let's do this one. C2 is a clockwise oriented circle of radius 3. So the radius 3 and clockwise circle. So that, okay, let's try to draw a circle here, radius 3. So it's passing here. Y is big circle. And, oops, okay, like that, like this. Okay. Oh boy. Okay. So we have circle like that. Now, clockwise oriented, so it's running there, right? And that is C2. Okay. for this one, we want to determine whether the line integral is positive, negative, or zero. Okay. For this one, and mostly right now, for there is unit tangential vector t, and a vector field is now given along that direction. That means that for along with f and t dot product must be negative because the angle is larger than pi over 2, and so that the dot product is negative for each point, so that the integral along this closed curve is negative, right? At each point, the line integral that is defined in this way, that is now f dot t ds, of course, the same curve, but this one is all the way the angle between here f and t is obtuse, so that dot product is negative, so the integral is negative, right? For this part, you can figure it out quite easily. Okay, that's the end of the section. Thank you.